Hello students, welcome to the last segment of our class. We're going to devote the next few weeks to the study of the class NP. We're going to introduce the theory around this class, and we're going to talk about problems that belong to this class. This is one of my favorite topics because it doesn't center around designing algorithms to solve problems, but more about identifying and proving that certain problems are yet too hard for us to solve. To do that, we're going to precisely define the class NP and the class P. We're going to talk about the famous question of P equal NP. And we're going to talk about how we can, in a very precise way, how we can name a problem to be hard from the computer science point of view. Now, there are a lot of misconceptions when we talk about problems in computer science that are hard, or even when we talk about the class NP and we talk about problems that we cannot solve. And there are a lot of misconceptions precisely because this is a very this is a theory, or it's a segment of computer science that allows for a lot of misleading points of view. So we need to precisely define what it means to be hard in computer science, and also what it means to be a problem that we cannot solve in the terms that we want to do that. And I wanted to point out a few maybe simple ideas which are going to be key to this understanding. The very first ones are the following. Typically, when you solve a problem in computer science, you're presented with the setting and you need to find a solution. But the number of candidates, or the set of candidates that could be solutions for your problem, is typically of exponential size. Which means that if you start by checking one by one your possible solutions, it will take a long time. And we as humans, we don't want to do that. We don't want to devote a long time to just find a solution of a problem. We would like to be more clever than that and design an algorithm, a procedure that will, step by step, will reduce the size of candidate solutions, and eventually get into a set of solutions instead of just a pool of huge size of candidates. So we need to do better than that. Now, I've been saying that we will design an algorithm, and we have been in this class, every time we talk about the design, we have been measuring the running time. That is very much connected to this discussion we're having right now, because the running time is how long it takes to this design of us to reduce the pool of candidates to, well, the set of solutions. This set could be still large, but we are sure that the outcome is a solution. We want to do this efficiently. And efficiently means polynomial in the input size. We want to talk about that more often. But before, let me define the set of problems that we want to target, the set of problems that we want to solve by designing algorithms that runs in a reasonable time. So the discussion in the last few weeks is going to center around performance, meaning the running time of our designs, in the same way we have been thinking about it till now. And we want to do this for a certain class of problems. So what will be our problems? Well, think of a typical instance of a problem. You're presented with a problem, then you're presented with an input of this problem, and then we need to find a solution. Let me label this solution as S. Or we want to report if such a solution does not exist. Let me give you a familiar example, the minimal spanning tree. The problem is defined as give me a graph, and I will return a weighted graph, and I will return a minimum spanning tree. Maybe this input graph doesn't allow for a minimum spanning tree because, for example, may not be connected, and then you want to report also that this solution does not exist. These are what we call the search problems, except there is something missing that I wanted to add. So the universe of problems we're going to deal with are going to be these problems, those that we can either output a solution or report that such a solution doesn't exist, plus the following important property. We need to be able to check candidate solutions. And here is the formal definition I'm going to read from the slides. Given an instance I of your problem and a candidate solution S prime, we should be able to verify in polynomial time that S prime is indeed a solution to the instance I. What it means polynomial time here, I'm putting an asterisk there, that means polynomial time in the input size, in the size of the instance I that you're getting. Again, back to the minimum spanning tree example. If I give you a graph, I want you to be able to check a candidate solution in polynomial time on the size of this given graph. What is a candidate solution? Well, this is simply a solution that I may get through different ways, but I believe is a solution to my problem. I need to design an algorithm that it may not solve the problem itself, but it will check whether this candidate solution is indeed a solution. For example, if I give you the minimum spanning tree, I give you a graph, which is the instance I, and I give you a set of edges, and I tell you, students, this is a minimum spanning tree for the given graph. You should be able to design an algorithm that will check whether or not that set of edges, S prime, is indeed a minimum spanning tree. You will do that in the homework, and I will repeat that same sentence in a couple of slides. So this is the class of problems we're going to deal with, those we can check solutions in polynomial time. This doesn't mean solving the problem in polynomial time. We will see a lot of problems for which you are able to check solutions, but we don't know how to solve the problem in polynomial time. Solving means give me any input, I will be able to output a solution, or I will be able to report there is no solution for this input. Checking solutions involve getting an input and also getting a candidate solution for that input. That is what we call a search problem, those for which we can check whether or not the candidate solution is a solution or not. Now, you may be able to solve a problem in polynomial time. This is a special subclass of this universe of problems for which we can verify solutions in polynomial time. The universe is what we call the class NP, the set of all search problems. The subclass of problems that are search problems, in other words, we can verify solutions in polynomial time, and on top of that, we are able to solve those problems in polynomial time. That's what we call the class P. So now you have a universe that we call it NP, and within that universe you have a region, a subset, which we call the class P. So this is a subset of the class NP. It will be a great idea at this point, I feel, to see a couple of examples, to see examples of problems that live in this universe NP. So let me start with maybe this is also familiar to you guys. It's a graph problem, so we're fresh with graph ideas in our mind, and this is a famous problem, which is in popular folklore known as the K coloring problem. What is the problem? We're given an integer k bigger than 0. This is a natural number, and we're given a graph G, which is typically undirected. It doesn't really matter. What is our goal? Is to return a coloring of the vertices, coloring of the set V, which involve at most k colors, in a way that every edge get different colors on the end vertices of those edges. Okay? Of course, if k is a large number, for example, if you get more than V, many colors, you can paint every vertex with one color and your life will be solved, or your problem will have an easy solution. But if you get a few colors, few compared to the size of V, this problem is hard. You know, it may be challenging to get a solution, and I encourage you, if you haven't seen this problem before, to Google the 4 coloring problem, and it has a wonderful history and a wonderful solution that use machines quite fundamentally. Why this problem is in the class NP? Why is this a search problem? Well, let's verify that if I get an input, meaning if I get a k number and a graph G, and I get a candidate solution, I can verify in polynomial time whether or not that is a solution. What does that mean? That means that I will be given a k number and a graph, and also I will be getting a candidate solution. Now, a solution here is a coloring of the vertices. So that means I will get an assignment of k colors to the vertices of G. If you want, think that you're getting a function that is taking every vertex to a number from 1 to k. Every number represents a color, and then you're assigning a color to every vertex. What do we need to do to verify whether or not this is a solution? Well, one simple way is to go through the edges one by one. We will compare the colors at the endpoints of those of the vertices, or I will compare the colors at the vertices ending this edge. If they are different, I will move on to the next edge. I will do the same, and I keep doing this. If I find an edge with 2 vertices at the end of the same color, I will stop and I will report this is not a solution. If I conclude my loop, if I go through all the edges and every edge has two different colors at the end, I will report this is a solution. Every operation that I do here is basically a comparison, and this happens for every edge. So I have an order M verification procedure for the K coloring problem. So this is indeed a problem in the class NP. Notice that I gave you a way to verify whether or not a candidate solution is a solution. I never tell you how to solve the problem. If you give me the graph and the number K, I had nothing to do with this procedure because this relies on the coloring. I am also getting a candidate solution. So this has nothing to do with the solution of the problem in general. This is just verifying the or a candidate solution. Let me show you one more example. This is a very important problem, and we want to devote the next video to this problem or variants of these problems. So I may go a bit fast now, but we will retake or we will talk more about this problem in the next video. This is what is known as SAT. This is what is that is also known as the constraint satisfaction problem. What is this problem? Well, we're given a Boolean formula. What is this? Is a formula that takes as an input variables that takes value 0 or 1. This formula is written in conjunctive normal form. I will tell you in a second what that means, but we will abbreviate that from now on CNF, because typically the input of an SAT problem will be in CNF form. And the task of this problem is, given this formula, I need to find an assignment of the variables that evaluates to true, or I will need to return no if such an assignment does not exist. True here means, of course, value 1, and no will mean that every assignment of the variables will report a 0 value or a false if you want. So let me give you a concrete example. You are given a formula that we will denote by F. We are getting, this formula is getting as input x1, x2 up to xn many variables, and all these variables are getting values 0 or 1, and the output is also a 0 or a 1. The task is to get an assignment of the variables from x1 to xn such that the formula evaluates to 1. Or to say there are no such assignments. In other words, every single assignment reports or outputs a 0 for this formula. What is conjunctive normal form? Well, my formula F is written as the intersection, which we will logically use the symbol and we will denote that symbol with this triangle without a base if you want. And this intersection is happening between M clauses. What are these clauses? Each of those are disjunctions of the literals made out of the variables. Disjunctions means or, and literals is either the variable xi or the negation of the variable xi. To abbreviate all this vocabulary, we use a bar in top of the variable to refer to the literal negation of xi. Here is an example of a formula in CNF form, or in CNF, because form is right there. The function f, or the formula f, is taking variables from x1 up to x5. It's the intersection of 4 many clauses, which are the parentheses that you see here, and each of those parentheses is written as the disjunction of literals that are made of the variables. The very first clause is x1 or x4. The second one is the negation of x2 or x3 or x5. The third one is the negation of x1, and the last one is the negation of x2 or the negation of x3. What does this mean? This means that because we have an intersection of clauses, each of those have to be true in order for the formula to output the value 1 or to output a true value. And because we have a disjunction within the clauses, it is sufficient for one of those literals to be true within the parentheses to make that parenthesis equal to 1. In red, I gave you here an assignment of the variables that evaluates this formula to 1. And you can easily check that. For example, x1 equal to 0 means that the negation of x1 evaluates to true. And notice the playing with the language here. This expression, this literal x1 bar, means that I'm looking at the logical statement negation of x1. So for that statement to be true, I need to make my variable x1 to be false. And this is why x1 equal to 0 makes this clause equals to true or equals to 1. As you have seen so far, I will interchange between true and one and zero and false because, well, this is something standard in computer science. Let's briefly verify that this is indeed evaluates to true. X1 equal to 1, x5 sorry equal to 1 makes this clause equal to 1, because no matter what x2 and x3 are, I know that x5 is true already. So that makes this OR statement equal to true. Now x1 is negative or is 0, so I know this is not true, but x4 is equal to 1. So that makes the first clause equal to 1. And lastly, x3 is 0, so the negation of x3 is true, which makes the last clause equal to true. Each of the clauses in this formula is true. The intersection is also true. So this is a valid solution for my Boolean formula or for my problem, my SAT problem. The question is this problem in the class NP? In other words, if I give you a candidate solution, can you verify in polynomial time whether or not that candidate solution is or not a solution? What is a candidate solution here? Well, it's an assignment of the variables to be equal to 0 or 1. So if I give you a formula and I give you an assignment of the variables, can we check whether or not this assignment evaluates to true or not? Well, give me the formula. I know that my formula have m many clauses. Each of my clauses will have at the most n literals, because conjunctive normal form does not, avoids, and this is something I didn't include, so I will mention again in the lectures. You avoid to use the same variable many times, or you avoid using trivial statements like x1 or negation of x1. That's trivial because no matter what you assign to x1, you get a valid solution. We will avoid this in CNF for a formula. So if you give me a clause, it will have at most n variables. So I can go one variable at a time, checking if the given assignment evaluates to true. If so, I move on to the next clause and I do the same checking. And I keep doing this until I find a clause that evaluates to false, in which case I will report that this is not a solution, because one single clause evaluating to false is enough for the entire formula to evaluate to false. This is an intersection, remember? And if every single clause evaluates to true, we're good. We report this is a solution. How long this will take? Well, I have to do order n many operations, order m many times. So the total running time will be order m times n, which is polynomial in the input size, because the size is the number of clauses m and the number of variables n. So the problem SAT is indeed in the class NP. So we have two problems in the class NP, the K coloring problem and the SAT problem. Let me mention one more that you will prove in homework for A is in the class NP. This is what we will denote by MST, the minimum spanning tree. Given a weighted underrated graph G, find a minimum spanning tree, or return no if such tree does not exist. This is the problem. What you need to do in the homework is, given a graph and given a candidate solution, verify in polynomial time that that is indeed a solution, or simply report this is not a solution. That's what it means to verify whether or not the candidate is indeed a solution. I'm going to mention one more problem that is familiar to you, and this is the Naxide problem. We saw this problem, or you saw this problem with Professor Avernetti before, and you saw a dynamic programming solution for this problem. Remember the setting. You are given a set of objects. I'm going to list the objects from 1 to n. These objects has a weight, w1 to wn, and also a value, v1 to vn, and you're also presented with the capacity that I'm going to denote by capital V. And what you want to do is you want to find a subset S of the objects such that the sum of the values of those elements that you choose is maximal, but keeping the sum of the weights below the capacity B. So you don't want to violate that constraint, sorry. You saw a solution using dynamic programming to this problem. And the question now is this problem in the class NP? Well, that is given as an input of this problem, a set of weights, a set of values, and a capacity V, and given a candidate solution, given a subset S of the objects, can we check in polynomial time whether or not this set maximizes the profit? And here enters a very important example, because this problem has a very special thing that the previous problems maybe didn't have. Maybe the MST did, but not the SAT, not the K coloring. We are optimizing a function here. We are maximizing the profit. So if I give you a set of objects, you can easily add the weights together and verify whether or not this sum is less or equal than b. That gives you the checking of whether or not this is within the capacity constraints. But how do we verify that this is maximal? How we verify the profit is maximal? I will let you think about that, and if necessary, we will talk about that in lecture. But I'm going to tell you now that we don't know how to verify in polynomial time whether or not this candidate solution is indeed a solution, because we don't know how to maximize or to check that this maximizes the profit. Okay, remember that to check that these guys maximize the profit, you need to prove that any other set of objects or any other subset of objects within the capacity V does not get a profit bigger than the profit outputting by S. And that means essentially checking every other subset. We don't know how to do that for the knapsack problem. So the knapsack problem is not in the class NP. There is an important feature here that is worth mentioning, because you may be thinking, well, I can run the dynamic programming algorithm and I will get the maximum profit, and then I can compare that to the profit of my candidate solution. But remember that the knapsack dynamic programming solution is not polynomial. That runs in exponential time on the input size. So we don't know really how to check, how to get a real idea of the maximal profit in this knapsack problem. So with this discussion, I want to show you a picture. Remember, knapsack is not in the class NP, and I want to show you a picture of the universe NP that we have so far. So far, we have this big universe, which is this outer circle. In the class NP, we have problems SAT, the K coloring, and we have the minimum spanning tree problem, which actually lies within the circle that I will denote the class P. But we have knapsack, which is a problem that lives out there. So there are many problems in the universe, not only the problems in the class NP. There is a wider universe out there, but this is the picture we have so far. So I hope this picture gives you a good sense of what the class NP is. The next question is how we identify difficult problems in this class. How we identify, for example, that the problem MST is actually not so hard to find a solution. We actually saw polynomial time algorithms to solve this problem, but maybe other problems are very hard. How we define a hard problem in the class NP. Where for that, I'm going to give you an informal idea first, and then we're going to jump into the most important definition of this video. What it means to be hard in this class? Well, I'm going to think that a problem is going to be hard if I am able to solve this problem in polynomial time, I will be able to solve all the problems in the class NP in polynomial time. So this problem is so hard that solving it will allow me to solve every other problem in the class NP. To make this idea formal, I need to be able to connect every other problem to this very hard problem. And we're going to do that through the concept of reduction. And reduction, let me stress this out again, is the most important definition in this video. When you walk away from your computer tonight or today, or whatever time you're watching this video, you need to remember this slide. What is a reduction? We are given two problems A and B, and we will say that problem A reduces to problem B if we are able to build two polynomial time algorithms that we're going to denote by F and H for this definition, such that an input of problem A is given, input I, and I am able to use algorithm F to map this instance I to an instance F of I of problem B. And then H is an algorithm that maps a solution of problem B for input F of I to a solution of input I of problem A. That is a lot of wording that I'm going to visualize for you now. But before I move on, we're going to write A reduced to B by simply putting an arrow from A to B. What is this definition in visuals, in a more concrete picture? Think that you have two problems, A and B. Problem A is outside and problem B is within. You're given an instance of problem A. You're aiming to solve problem A. And then what we do to aim to solve this problem is we're going to use the procedure F, the algorithm F, to build an instance of problem B. that we're gonna call f of I. If you get that instance, then you can run that through some black box that you may have for algorithm V. That will output a solution S of this input f of I, or maybe you simply report there is no solution for f of I. If that is the case, the second one, if you have no solution for f of I, you need to be able to check that there are also no solution for problem I. This is now for input I of problem A. If you get a solution for input f of I, then you transform that solution through the algorithm H to a solution of input I for problem A. In other words, reducing A to V allows you to, given a black box that solves algorithm problem B, given an algorithm for problem B, you are able to solve problem A. And if the algorithm for problem B runs in polynomial time, because every other procedure also runs in polynomial time, you get a polynomial time solution of problem A. So solving B allows you to solve A. If you reduce A to V, that means that V is as difficult as problem A. Now it is important that your reduction respect the no solution situation. If you input f of I to this black box and you get a no solution, your input I of problem A must have no solution as well. So this function or this algorithm H must have like this if and only if property. If I has a solution, then f of I has a solution, and vice versa. F of I has a solution for problem B, then input I has a solution for problem A. If you build these two algorithms, F and H, then you're reducing A to V. And if you're a bit lost by the wording of this presentation, do not worry. We're going to spend the next few days talking about how to find reductions, and this will be the key to identify problems that are going to be very hard. Now imagine that you find a problem B such that every other problem reduces to it. That means that if you solve problem B in polynomial time, you will be able to solve every other problem in the class NP by solving B, by using this reduction strategy. That means that the problem B is as hard as every other problem in the class NP. That is what I will define, that is what we define as a very hard problem in the class NP. So let me give you a formal definition. A problem B is said to be NP hard if for any problem A in the class NP, we have a reduction from A to B. Furthermore, if my problem B in the class is in the class NP and is also NP hard, we say it is NP complete. If you take the definition of reduction and this definition from today's video, you're in excellent shape to move on to the next video. But before you do so, let me show you one more picture and one concluding remark. The picture is now the following. A problem that is NP hard looks like this blue dot here. Every problem in the class NP can be reduced to that problem here. But also it may look like this problem B in the class NP. Every problem in the class NP reduces to that problem B. Notice that I have no obligation to reduce problems outside of the class NP to NP hard problems. We don't have to do that. In particular, I don't have to reduce knapsack to this problem B to being able to say that this is NP hard. I have to reduce every problem in the class NP to that problem. This is still a very strong idea. Like, we need to reduce every problem in a universe of problems to one single problem, but do not worry, we will simplify that quite a bit. And let me give you one more picture that puts our universe in a more detailed map. My universe now looks like this. We have the class NP, which is this circle over here. Within that class, we have the class P, which is a subset of the class NP. And now we have the NP hard problems. These are the problems for which every problem in the class NP reduced to them. This may intersect the class NP, and the intersection is what we define as NP complete. These are problems that are NP and also NP hard. So they live in the class NP, they can be verified, candidate solutions can be verified in polynomial time. But if I solve these guys, I will be able to solve every problem in the class NP because I can reduce every problem to these guys. And now, to conclude this video, What it means P equal NP? This big question that we have been listening to computer science to talk about since we were babies. Well, the question is it true that every problem in the class NP can be solved in polynomial time? We don't know that yet. But we do know now that if I solve one NP hard problem, just one, using the reductions, we can solve every problem in the class NP also in polynomial time. So solving one NP hard problem in polynomial time implies that P is equal to NP. That is the big question. And if you ever come up with a solution, I always tell this to my students, mention your Georgia Tech professor in the acceptance speech of the award that you will get. You will get many awards, but at least in one speech, just mention my name. That will be enough for me. With that idea in mind, I'm gonna let you here. I'm gonna move to the next video. Here's what you need to remember, and I will remind you of this at the beginning. Remember what a reduction is. What is the definition of the class NP and the class P, this subset, and what is the definition of the class NP hard? The intersection of NP hard and NP is what we call it NP complete. We're going to use reductions to identify NP hard problems, and we're going to devote, again, the next few videos to talk about really hard problems, the problems in the class NP hard. I see you in the next video.